This is Calculus 3 video lecture number 34, Stokes Theorem. Now, if you'll remember, Green's theorem related a double integral over a region with a line integral around its boundary in the plane. And Stokes' theorem is going to allow us to relate a surface integral over some surface S with a line integral around its boundary in space C, sometimes referred to as del S, the boundary of the surface. So using Stokes' theorem, the orientations of both the surface and its boundary curve are important. And if you look here at the diagram, remember our standard orientation is outward for our unit normal, or upward if you're in a plane. And when you're transversing the curve, just imagine here's this little person. Hopefully you can see them walking along the curve. And when you're in the positively oriented direction that's counterclockwise, the surface should be on your left-hand side, okay? So if you ever get confused, just imagine yourself walking on the boundary and make sure that the surface is on your left. So here's Stokes' theorem. Let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C with positive orientation. And then let F be a vector field whose components have continuous partial derivatives on an open region containing S. Then, the line integral over C of f dot dr, remember, what does this line integral represent? Yes, it represents work. This is equal to our surface integral, so double integral over S of the curl of f dot ds, that S is the vector quantity. So then remember, we end up computing this as the double integral over the surface S of the curl of f dot n ds. Now notice that if your surface S is in the xy plane, so it's not going to be a surface in 3 space, it just lives in the xy plane, then your vector field would only have components P and Q, right? It would not have a third dimensional component. And your standard unit normal would be going upward because you're working with a surface that lies in the xy plane. So your positive orientation would be upward. So the components of your unit normal would be 0, 0, 1. And we know that vector. That's a special unit vector k hat. So if we wanted to compute the work along the curve C that bounds your region S, we would compute the line integral of f dotted with dr. And then I know from Stokes' theorem now I can rewrite this as double integral. And then since we're only working in the xy plane, this is just going to be a double integral over some region D. And ds is going to be dA since we're working in the xy plane again. So I have D here, curl of f dotted with k hat dA. If you'll remember, we actually showed this equality in the video on Green's theorem if you want to reference it. And then I can apply Green's theorem and rewrite this as the double integral over D of del Q del X minus del P del Y dA. And yes, this is good old Green's theorem. All right. Good. So if you want to think of it in a sense, Green's theorem is just Stokes' theorem, but applied to surfaces in the xy plane. Okay, let's verify Stokes' theorem for the following vector field with components 2y, negative z3, and then S, our surface, is the positively oriented surface of the portion of z equals 4 minus x squared minus y squared that lies inside the cylinder x squared plus y squared equals 1. Okay, so when they're asking us to verify Stokes' theorem, what we have to do is go back to the definition and compute the work 2 ways. The first way is by computing the line integral, and then the second way would be by computing the surface integral. Okay, so make sure you read the directions carefully, since verifying means do both. Okay, let's start off with the line integral. And if you'll remember, here's our vector field. So I'll call the components P, Q, R. And we evaluate the work by computing the line integral over C, the boundary of the surface of P dx plus Q dy plus R dz. Now I need to know what the boundary is of the intersection for the surface, the two surfaces that are given here. Okay, so C is going to be the boundary of intersection of Z equals 4 minus x squared minus y squared and x squared plus y squared equals 1. So let's just solve this out here. I could substitute in x squared plus y squared equals 1 into the equation of that paraboloid, and then I'm going to be left with z equals 3, right? Because this would just give me -1 now. Okay, and so let's see what that would look like. This is the curve of intersection here, x squared plus y squared equals 1. Let's draw out everything. Even though it doesn't ask for it, you need to draw out a picture for every problem that you do. Okay, x, y, z. So the paraboloid's been shifted up 4 units. And then in the xy plane, we know it's going to trace out a circle of radius 2. Very good. All right. And then we have this cylinder, radius is 1, and they intersect when z is 3 right here. Okay, so our surface S is the portion of the paraboloid that lies inside the cylinder. So can you identify what S is? This is the portion of the paraboloid that lies inside the cylinder. That's S. Okay, and the boundary curve C, let me highlight it in a different color so you could see it. This is C, the boundary curve right here. Right, that's where their intersection was at z equals 3, and it's just the circle x squared plus y squared equals 1. So I need to represent it parametrically so I can compute the line integral. So if c is x squared plus y squared equals 1, remember we need standard positive orientation. So I'll define x to be cosine of t, y will be sine t, and then z will be 3 here. That means dx is going to be negative sine t dt. dy would be cosine of t dt. And then dz is just going to be 0. And then t will be bounded between 0 and 2 pi, right? So we trace the boundary curve once. Good. So let's go ahead and set up this line integral now. So I will have line integral over C. Let's go back to our vector field. So P is 2y dx plus Q is negative z dy plus R is 3 dz. Very good. Now let's replace everything so it's all in terms of t. So limits of integration are going to go from 0 to 2 pi. Then I have 2 times y is sine t. Dx is negative sine t dt. And then I have minus z, so minus 3 dy is cosine t dt. And then I have plus 3 dz, which is 0. So what are we left with? Integral from 0 to 2 pi. The first term is going to be negative 2 sine squared t minus 3 cosine of t dt. And then I'll let you verify this comes out to negative 2 pi. Okay. Just need a little half angle identity for that sine squared, and the rest is smooth sailing. Okay, but we need to verify Stokes theorem. So next I'm going to evaluate the surface integral and show that the results are equal. Okay, so if you'll remember, F, our vector field, had components 2y, negative z, 3. So in this integral I need the curl of F. Now we're actually going to use that curl business. Okay, So we have I hat, j hat, k hat, del x, del y, del z, and then put your vector field in the bottom row, 2y, negative z, 3. And let's see, what do we have here? So partial derivative of 3 with respect to y, that's 0, minus partial derivative of negative z with respect to z, that's negative 1, which is 1. Next component, go this away, 0, 0, okay. And then the last one is negative 2. Okay, now from here, let's remember what surface are we using? Keep it straight. The surface S is determined by the paraboloid, not the cylinder, okay? So S is determined by Z equaling 4 minus x squared minus y squared. Now what am I going to use for my normal? Remember, you have two options. Either you have positive partials for the first two components and a negative one for Z, or you have negative partials for the first two components and a positive one for Z. We'll look back at your picture. Standard orientation, standard positive orientation is outward or upward. And just imagine that you're walking on the surface, okay? You're not walking on the boundary, you're walking on the surface. And when you get to the very top of the surface, you're right here. Outward or upward is pointing in the direction of your head, right? So for n, determine the last component first, determine the one that's constant. It would be a positive 1, right? That would be upward. If it was negative 1, that would be pointing inward to the surface. And then from there, you know that the other two components are going to be the opposite sign. So you'd have negative partial with respect to y, negative partial with respect to x, okay? So coming back here now, I know I'm going to have, since z is defined in terms of x and y, I'll have negative partial with respect to x, negative partial with respect to y, and then positive 1. So always determine this sign first, and then the other two will be opposite. And then if your surface was defined as a function of, say, x and z instead, right, then you would have to first figure out if y needed to be positive or negative 1, and then the other two components would be the opposite sign, okay? Good. So let's go ahead, figure out what n is going to be now. So partial derivative of our surface with respect to x is negative 2x, but then I'm going to switch the sign, so that's positive 2x, positive 2y, and 1. Okay, then you take the curl of f and you dot it with this normal. So we will have, you remember where the curl of f is? It's right here. Dot it with the normal, we'll get 2x plus 0 minus 2. So 2x minus 2. So that's what we're going to integrate. Okay. So that means the work is going to equal, we have surface integral. This is curl of f dot n. But remember, we need to make n a unit vector, so we divide by its magnitude, and then you have ds. But then that magnitude cancels out, right? Because we know ds has that same expression with a dA attached to it. And then you end up just integrating over some region that you project the surface in. In this case, we'll use the xy plane. So my region D ends up being the unit circle. Okay, I'm going to go back to the picture. Hold on. So your region D is down here in the xy plane. If you project that surface in the xy plane, then you can just integrate over the unit circle. I will label that that's D so we know. Okay, and the integrand stays the same. It's just 2x minus 2 dA. Well, how do you want to evaluate that integral? I think it's a great time to go polar, right? So let's set it up. Limits for theta should be 0 to 2 pi. Limits for r, 0 to 1. And then replace x with r cosine theta minus 2. And then remember, dA is r dr d theta. Okay, and then I'll let you come to the exciting revelation that this is also negative 2 pi. So the result was the same using both methods, which means we verified Stokes' theorem for this particular problem. Yes, the result was the same. Using both methods. It doesn't mean we proved Stokes' theorem. We just verified it for this particular method. Okay, now interestingly, Stokes' theorem, it tells us that the value of the surface integral of the curl of f on S depends only on the value of that vector field on the curve of the boundary. So it follows that if we have two surfaces and they have exactly the same boundary curve, C, then the values of the surface integrals of the curl of f on the two surfaces will be equal, which might not seem intuitive at first. So here I'm going to show you an example. Like, say you have a surface, some paraboloid. Maybe we'll draw a nice paraboloid. I said a nice one. What am I drawing? Okay. Oh, much better. And then I'm going to intersect it with another surface. Let's do a half cone opening downward. Okay. So this will be surface 2. This is surface 1. And you can see their intersection is this region here. But the boundary curve would be the same for both. So in this particular instance, if you're computing the work done, or the value of the surface integral of the curl of f on S, even though the two surfaces aren't identical, their boundary curves are, and so they would have the same value. Okay? Good. Let's move on and look at a couple more examples. So, find the surface integral of the curl of f dot ds. Remember, what does this represent? That's right, work. For the following vector field, where S consists of the four sides of the pyramid with vertices 0, 0, 0, that's right here, 1, 0, 0, 0, 0, 1, 1, 0, 1, and then 1 half, 1 half, 1 half, that lie to the right of the xz plane, oriented in the direction of the positive y-axis. Okay, so let's think here about how we would set up the problem, and then I'll show you a little way out of it. All right, so they told me S consists of the four sides of the pyramid, so it's open in the back. Okay, if you were to compute this directly, you would have to do 4 surface integrals. One on each face of the pyramid, yes? Okay, and then each surface could be done or evaluated using 3 line integrals. So let's see, say this is surface 1. And remember, our standard orientation is counterclockwise. So it would go 1 line integral this way, 1 line integral this way, 1 line integral this way. Then you would move on to the next face, maybe surface 2. So you'd have a line integral this way, and then this way. And then you would repeat, right? So there's the one face that's in the YZ plane, and then this slanty one here, right? That would be your fourth one. But did you notice that 2 of the line integrals right here cancel out from surface 1 and surface 2? And similarly on the other side, right, for surface 3, you would have a line integral going in the opposite direction that would cancel out. In fact, everything on the interiors there is going to cancel out. So we would set up 3 line integrals for each of the 4 surfaces, which would be 12 total, but 8 of them would cancel out. Which ones don't cancel out? Only the ones that are on the back here. These line integrals would not cancel out. So this leaves 4 line integrals remaining. Everything else cancels out. Now, the 4 remaining, let's think about them. They bound a square in the XZ plane. And so let me shade in that square in the XZ plane. Okay. Very good. I'll circle it in green here so you know that it matches the graph. And this square is a piece of the plane y equals 0. Okay, now I took their liberty of finding the curl of f in my spare time. And it is 2xy minus e to the z, negative y squared, and negative x. And so on the surface, y equals 0, this becomes negative e to the z, 0, negative x. And what would we use for our unit normal? Well, let's think about it. You're on that little square in the XZ plane. Standard positive orientation is outward, outward. So outward would be this away, people. That would be n. So what would the components be for a vector that points in the negative y direction? It would be 0, negative 1, 0. Okay, so if I take the curl of f and dot it with n now, I'm going to have 0 plus 0 plus 0. Ooh, that's 0. So what does that tell me? The work done, or the surface integral of the curl of f dot n ds is equal to 0. So we didn't actually have to integrate a single thing, and we got the answer just by thinking about it. Okay, but maybe you want some more practice, right? Don't worry, I got you covered. Use Stokes Theorem to evaluate the work as a line integral, where f equals z squared y squared xy, and c is the triangle with vertices 1, 0, 0, 0, 1, 0, and 0, 0, 2, oriented counterclockwise when viewed from above. Okay, so here's the thing. They're telling us to use Stokes Theorem, meaning do not compute the line integral directly. No, we have Stokes Theorem, which tells us that instead we can use a surface integral. So this is a triangular surface. I'm going to sketch it in just a second, but the idea is instead of 3 line integrals, we do 1 surface integral. Okay, good. So let's draw the surface out. 1, 0, 0, 0, 1, 0, 0, 0, 2. Okay, so here's the surface. And then they told us the orientation is counterclockwise when viewed from above. Okay, so you decided to come hang out up here, look down at this surface. Orientation is this way. Okay, good. So here we go. That means I'm going to evaluate surface integral of curl of f dot n ds. Okay, let's first get the curl of f. I'll just give it to you, okay? Hopefully you have enough practice in evaluating curl in the other sections so we can move on with our lives. You'll get x, 2z minus y, and 0. Where to go from here? Remember, you're going to evaluate a surface integral, a double integral, so you only want two variables in the game. So look at the surface, right? I need the equation of that surface so I can get rid of one of my variables. And I showed you that sneaky way to come up with the equation of a plane so you're not wasting time making normal vectors and crossing them, right? So you figure out what's the least common multiple for all the intercepts. It's 2. So you set the equation equal to 2. And then since the x-intercept is 1, then we need a 2x in front of it. The y-intercept is 1, so I need a 2y. And then the z-intercept is just 2. So what does that mean? Well, I can solve z in terms of x and y, 2 minus 2x minus 2y. And then now I'm going to use this expression and substitute it in for z into my vector field. Well, into the curl of f, excuse me. So we have x, 2 times 2 minus 2x minus 2y. This is going to be 4 minus 4x minus 4y minus another y, 0. Okay, very good. Now, what about for n? So, I have z solved in terms of x and y, so I want you to first figure out, should the z component be positive 1 or negative 1? All right, now imagine you're on the surface, and look at where this little man is, all the way at the top of it. Positive outward orientation is going to be upward, right? Or outward from the surface. And just imagine if you were walking on the edge there, the z component would have to be positive. So this is going to be 1. Negative partial with respect to y, negative partial with respect to x. You could also use the right-hand rule, curl your fingers in the direction of the arrows on the curve, and you can see that your thumb points upward. So the z component should be positive for that normal. Okay, so curl of f dotted with n is going to give us, you just do a little dot product, 2x plus 8 minus 8x minus 10y plus 0. Nice, I like it. Negative 6x minus 10y plus 8. Okay, good. So everything's in terms of x and y. When I evaluate this surface integral, right, I'm going to do a double integral over whatever region I want. Let's use the xy plane. That seems to make the most sense. And d, if you'll recall, is the region that you integrate over. So there's d down there. That's d. Okay, so here's 1. Here's 1. I think you can handle this, right? This is the equation x plus y equals 1. So you could set it up with constant limits for x or y just as easily in this integral. Let's just put x on the outside. Why not? So here we go. This is the work, surface integral of the curl of f dotted with n ds. These are my limits for x, 0 to 1. Limits for y, 0 to 1 minus x. Then you're going to integrate negative 6x minus 10y plus 8. I set it up dy dx. And it's 4/3. Voila. Did you like it? Fun, huh? Everything comes together. I'm telling you. Everything comes together. Okay. Couple more, and then that's it. Use Stokes Theorem to evaluate the surface integral of the curl of f dot ds with the following vector field, where S is the surface of z equals x squared plus y squared, so that's a paraboloid. Inside the cylinder, x squared plus y squared equals 1, oriented upward. Okay, so in this case, if they're saying use Stokes Theorem to evaluate a surface integral, that means instead we're going to find the work using a line integral on the boundary. Okay, so I'll set it up. This is P, Q, R. So we would have P dx plus Q dy plus R dz. Okay, now let's draw the surface. So we've got a paraboloid and it has to live inside a cylinder. Not bad, not bad. Let's go ahead and find their intersection first before we do that. So C is going to be my curve of intersection that's bounding the surface. Intersection of z equals x squared plus y squared and x squared plus y squared equals 1. Well, this doesn't take much solving, right? It just happens when z equals 1 along the unit circle. So let me draw it out. So say this is 1, 1, 1, okay? Here's the paraboloid. And that's going to be the curve of intersection. So the paraboloid keeps opening. We're not interested in that part. And then we have this cylinder. That goes up, 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 and down. Not interested in that, right? So S is the surface. It's just the part of the paraboloid that lives inside the cylinder. This whole thing, and the back part too, right? Okay. All that back there. And C, my curve of intersection, is this bright green piece here. Okay. So standard orientation is going to be counterclockwise. So we can parameterize this very easily, right? So C I can represent with x equals cosine t, y equals sine t. That means dx would be negative sine t dt. dy would be cosine t dt. Oh, excuse me, and z is 1. So dz would be 0. And then t needs to range between 0 and 2 pi. Okay, so it's line integral time. Here we go. So we have, writing everything in terms of t, limits from 0 to 2 pi. All right, first term is y squared z dx. So y squared is going to be sine squared t, z is 1, and then dx is negative sine t dt, plus xz, so that's going to be cosine t times 1, dy, which is cosine t dt, plus, I know dz is 0, so everything's going to be 0 on that last term. All right, and then now I'm left with negative sine cubed t, ooh, that's good, plus cosine squared t dt. You just pluck off one of those signs, change the sine squared to 1 minus cosine squared. You should probably be able to do that little u sub in your head, and then you just bust out your half angle identity for that guy, and you'll get pi for your answer. You should. Okay, good. Last example, here we go. So use Stokes Theorem to evaluate the work, but instead of using a line integral, we're going to use a surface integral, right? Just do the opposite of what they say if they're asking you to use Stokes Theorem, where your vector field is given as follows, and C is the curve of intersection of z equals y squared minus x squared. Do you know what this is? It's our beloved saddle. And x squared plus y squared equals 1. We know what that is. That's a cylinder. Oriented counterclockwise as viewed from above. Okay, I promised you wouldn't have to draw a saddle in this class, okay? And I'm not going to lie. So we're just going to weasel our way around it and still set up everything for our surface integral, okay? Now, what is the surface that's determining the region that we're going to integrate over? It's the saddle, right? The saddle is the surface. Z equals x squared, or y squared minus x squared, excuse me. Okay, so I need a normal. Remember, positive orientation is outward or upward. So you have that saddle, and pretend you're standing on it. The easiest thing is to imagine yourself standing like at a min point or a max point. And remember, we have a saddle point on a saddle. How clever. So positive orientation, which way is your head pointing? Upward, outward? The z component would be positive, right? So what does that mean? Then you would have negative partial with respect to x, negative partial with respect to y, positive 1. So opposite of the partial with respect to x would be positive 2x. Then this would be, negative 2y and 1. So we've got our outward unit normal, or just our outward normal. We'll make it unit in the integral. Okay, then we need the curl of f. Here's f. I too had a lot of spare time and computed the curl. It is x, negative y, 0, believe it or not. So curl of f dotted with n would give us, look what a cute dot product you get, 2x times x, that's 2x squared. And then negative y times negative 2y, oh, I love it, plus 2y squared, plus 0. All right, so here we go. We've got our surface integral, curl of f dot n ds. Okay, what is going to be D, the region that we integrate the surface over? Well, it's going to be in the xy plane. Have you noticed already? D is going to be the unit circle. Okay, so we've got double integral over D, which is our good friend, the unit circle. And we've got 2x squared plus 2y squared dA. Is this just screaming at you to go polar? I hope so. So you're going to take that 2 out. Limits for integration are going to be 0 to 2 pi for theta, 0 to 1 for r. And then x squared plus y squared, that's r squared. And then remember, dA gives you another r dr d theta. All right, and this comes out to be pi. I swear they're not all going to be pi. It just worked out that way with the examples that I'm doing now. Okay, good. So that concludes the lesson on Stokes Theorem. Can you believe it? And then the very last video for all of Calculus 3 is coming up next. It's on the divergence theorem. So stay tuned. Don't forget to give this video a thumbs up, and please subscribe if you haven't already.